Hi, everyone. Welcome to this new week of Astronomy 236, the history of matter in the universe. In this lecture bite, I'm going to be talking to you about special relativity. Like quantum mechanics, special relativity is another way in which we've updated the theory of classical mechanics, which we used to describe physics for hundreds of years. I want to set the stage. In the late 1800s, there was a crisis in physics, and I'll explain to you what the problem was. So imagine that you have a fellow who's riding along inside, or in this case, on top of a car, and he throws a basketball from the car at 20 miles per hour. So if the car is standing still, the basketball is thrown at 20 miles per hour, and we can measure that. If he's moving along in the car, he'll throw the basketball at 20 miles per hour, and it'll move away from him at 20 miles per hour. It doesn't really matter whether or not the car is moving or not for him to see the motion be relative like that. Now, if the car is moving and I'm standing on the side of the road and I watch this fellow throw the basketball, if the car is moving at 20 miles per hour and he throws the basketball at 20 miles per hour, then I see the basketball moving at 40 miles per hour. The speed of the basketball is added to the speed of the car. This is all well and good. It makes sense. In classical mechanics, what you do is you add the speed of the car to the speed of the throw. And this is kind of what we observe in everyday life. It's pretty intuitive, like a lot of other things in classical mechanics. In this clip you can see here, if you get a running start when you throw a football, you can throw that football further. It makes pretty good sense. So here's the problem. So let's imagine a different scenario. Instead of having a fellow in a car throwing a basketball, let's instead imagine that he's shooting a laser beam at the speed of light. This is light coming out of this laser gun. The theory of electromagnetic waves predicts that the speed of the light in a vacuum is constant no matter what, no matter who's observing it, and no matter how fast the person who is releasing that light is moving. So let's see what happens when the car is stationary and this fellow shoots his laser beam. The light leaves the laser and travels at the speed of light, c, or 670 million miles per hour. That's all well and good. But now let's imagine that we're watching this fellow shoot the laser beam from a car while we're standing still. So the car is moving at 20 miles per hour. How fast does the laser beam travel? It turns out that the laser, the light, still travels at exactly the speed of light, 670 million miles per hour. Not that plus 20 miles per hour or the speed of the car, exactly the speed of light, no matter how fast the person or thing that's emitting the light is traveling. So this is totally different from how objects behave in our experience and how they behave in classical mechanics. So essentially we have this clash between classical mechanics, which at this point in the late 1800s, early 1900s, had been the foundation of physics for 300 years, and this relatively new theory of electromagnetic waves, which was only developed about 30 years before this in the 1870s. And to resolve this issue, a fellow named Albert Einstein started thinking about this. And what Albert Einstein decided is that instead of trusting classical mechanics, the theory that has predicted so much successfully over the centuries, he wanted to throw that away and instead believe the prediction of electromagnetism, that light should travel at the same speed no matter what, no matter how fast whoever emits it is traveling. So instead of trying to figure out a way to make light behave the way particles in our experience behave, like baseballs and basketballs and footballs, Einstein decided to modify classical mechanics so that it describes light and other things moving close to the speed of light. So this is fairly straightforward to do once you have this idea. There's a little bit of math involved. But all you really have to do is assert that the speed of light is constant for all observers, anyone who's watching light travel, no matter what their speeds are. So to illustrate one of the consequences of this, I'm going to look from the top-down view. So here's your car again. Those little funny cylinders on the side are my attempted wheels. And this green person is shooting this laser beam, but now instead of shooting it forward, he's shooting it towards the wall, towards the far side of the car. And what we can observe is that it takes some period of time for the light to travel that distance. Now, I want to do the same experiment, but instead of watching it from the perspective of the car, I want to watch it from the perspective of someone standing on the side of the road as the car is moving. We can observe this event, and we can see the light also traveling as it hits the side. But from our point of view, outside of the car, the light has traveled further than it did inside the car. So this red diagonal line to the left is the path that the light took that we observed from outside the car. But if you're inside the car, it looks like the light took a much straighter path. It went directly to the wall instead of having to go sideways like this. So who's right? And what Einstein says is both people are right. It's other things that have changed. So the distance traveled by light in both cases is equal to the speed of light times the time it took for the light to go that distance. And since Einstein says the speed of light is constant and both observers are equally correct, then in order for light to have traveled less distance from the car's perspective, less time must have elapsed in the car. So this is really weird. What Einstein is essentially saying is that time slows down for objects and for people moving at high speeds. So if I get in a rocket ship and I start flying very, very high speeds, close to the speed of light, I will not age as quickly as other people would standing still. We've actually done similar experiments where we put clocks and put them in airplanes and fly those airplanes at high speeds, and we can see that this is true. And in fact, we've had astronauts who have who are twins. So here are two twin astronauts. One of them is Scott Kelly and one of them is Mark Kelly. Mark spent a year orbiting the Earth at high speeds, although not very close to the speed of light, in the International Space Station. And as a result of that, he aged less than his twin Scott Kelly did. So now Mark aged 5 milliseconds less than Scott Kelly did during that time. Now, this is a small effect. 5 milliseconds, no one's ever going to notice that. But the closer and closer this traveler gets to the speed of light, the more this starts to matter. So here's another consequence of that. All right, now we're firing the laser beam out of our car forward again. And let's say that it takes 5 seconds for the light to reach our target. The distance that the light traveled in those 5 seconds is equal to the speed of light times 5 seconds. But we know that time in the car is running slower than time outside of the car. So in the car, we would have perceived a smaller amount of time, but still light traveled the distance and reached its target in that time. So what this implies is that the light must have traveled a shorter distance from the point of view of the car. So as you're moving very close to the speed of light, distances along your path get compressed, they get stretched together, shrunk. Distances along the direction of your motion contract for people who are moving. So this is another very weird consequence of special relativity, but from all of the experiments we've ever done, it turns out to be true. So the last unusual and very important consequence of special relativity that I'm going to leave you with is hard to get at intuitively, but here's my best shot. So special relativity has some math that describes how time shrinks and how length compresses when you're moving. How time slows down, not shrinks, sorry. And this math breaks down when things start traveling at or near the speed of light. So when you get to the speed of light and you plug that into the equations, essentially the distance along the line of sight contracts to 0 and time stops. So this doesn't make much sense. It kind of is a meaningless thing. And besides, the math is such that when when you're trying to accelerate an object to the speed of light, you can never get there. You can keep applying more and more energy, and the harder you push, the faster you go. You will never actually reach the speed of light. So I want you to imagine this scenario. We have an object, we're trying to push up against this universal speed limit, and it's traveling at very, very close to the speed of light, 99.999%. We add a ton more energy, and it maybe changes the speed just a little bit. If we were traveling at slower speeds, adding that amount of energy would have changed the speed a lot, and therefore the amount of energy of that object's motion. But I've told you that energy doesn't it can never be created or destroyed. So where does that energy go? If we're traveling at the speed of light and we add energy to an object, what happens to that energy? And the answer, which is a little bit counterintuitive, but which has been shown to be extremely correct, is that energy and mass are interchangeable. So the energy that you apply to an object moving faster and trying to push it faster as it approaches the speed of light essentially starts behaving like mass and makes it harder to accelerate that object. So what Einstein discovered and figured out is that energy and mass are interchangeable and that they have an exchange rate. And that exchange rate is E equals mc squared, the famous equation. The energy that is in an object is equivalent, can be changed back and forth between the mass of that object with an exchange rate of the speed of light squared. So one of the consequences of this is that because the speed of light is very, very fast, if you square that, you multiply speed of light times itself, you get something even bigger, even larger. A tiny amount of mass has a ton of energy. So there is so much energy in all of the mass that we have around us. And we have used that for our energy needs in the 20th century. And that'll be described in the next lecture.